Hello guys, how are you doing today? Today we're gonna talk about fluid pressure, which is a little bit more of what you learn in physics when you study pressure and Archimedes principle and buoyancy, and then we're combining it with the concepts that you learn in statics about centers of gravity, centroid, center of volume, and which is really interesting because it applies to a bunch of real life structures like dams or even pools. Let's start the lecture about that. So, fluid pressures. Fluid pressure, remember, first is based on Pascal law, and we deal with fluids, of course, and we assume those fluids are going to be incompressible. Incompressible fluids, meaning liquids, basically. That's what we're going to do. This part is not necessarily true because I'm gonna just make a comment really quick that we apply the same principle that we're learning here for some soil type of structures, like when we study earth dams, or when we study even the pools again. So liquids. If you remember this from physics, and we already also talked about that earlier during the semester, if you have any surface submerged, and I remember we were discussing about a pool, and let's say this is the cross-sectional area for the pool, and this is the level of the water here. The level of the water is here. We said that if this depth is h, the depth of the pool, remember I'm doing a cross-sectional area, so the pool or the fish tank is going in that direction. So if this depth is h, and the specific or unit weight of the liquid, in this case of the water, remember unit weight also, unit weight is just the density multiplied by gravity. So if gamma is the unit weight, the pressure at any point is going to be equal to gamma. If you measure the distance y from here, the pressure at this point is going to be equal to gamma multiplied by that distance, or that submerged distance y. At the bottom of the pool, or at the bottom of this tank, the total pressure then is going to be gamma h. So the pressure here at the bottom, pressure inside, of course, inside the tank, is going to be gamma h. Gamma h. Gamma unit weight, h is the depth. And at the top, I know it's atmospheric pressure, but we are not considering atmospheric pressure here, and we consider atmospheric pressure like 0. So the distribution for the pressure is linear, and it's going to be like that. And that pressure is going to be exerted everywhere or anywhere in this direction. This is with the walls. Same thing happens in this other side of the tank. Now if you want to calculate, once again, now imagine this has a I don't know, a finite length in this direction, a finite width for the tank in this direction, and you call that distance, and let me do the same thing here also, finite distance like that, and then you call this distance b. This is b here. Then this is not going to be just a two-dimensional triangle. It's going to be like a prism, and it's going to be a 3D prism in this way, acting like that, acting like that. And if I want to calculate the total force coming from this pressure, the total force is just going to be equal to the volume of the triangle. Now you can simplify that by assuming that this dimension is equal to this dimension, and then we just calculate the force. If this is a triangular distributed force, the resultant force coming from this triangle is going to be acting somewhere here. Let's say that this is the resultant force, and you learn how to calculate that resultant force. We have been using that for distributed loadings in beams, for example. And that resultant force, is just going to be the area of this triangle. What is the area? Base, which is H, times the height, which is the pressure, in this case gamma H, divided by 2. That means that the resultant force in this phase is going to be equal to gamma H squared divided by 2. Now if you want to calculate the total resultant force is going to be just this multiplied by B. So I'm going to call this total resultant force like that. It's going to be B, if B is constant of course, or gamma B H squared divided by 2. Now if we are talking about areas and just this phase, what is the resultant force applied? Remember, this is a triangle, so it's going to be 1/3 of H measured from the right angle, or 2/3 of H measured from the acute angle. So the location is going to be of the resultant force 1/3 of H from the bottom, and if it's this one, it's going to be at the same level location, but it's going to be also at the center of the surface. So it's going to be just two coordinates in this case. If this is rectangular, well, it's going to be half of the distance in this direction and 1/3 of H in that direction. This is the basic principle. Now if you study the bottom, because if the bottom, all the points are at the same location, at the same point, and there is no change in the depth here, this is going to be a rectangular distributed load at the bottom, like that, where the total pressure at this point, or at this point, is going to be the same as here, gamma H, but the total force then on the bottom will be acting here. Resultant force at the bottom will be acting there, and the resultant force at the bottom will be only this distance, which I don't know, you can call it L if you want to, L multiplied by gamma H, because it's a rectangular force, a rectangular distributed force. So the resultant force at the bottom will be gamma H times L, and if you want the total, you just multiply this by B. Location of this force at the center of the structure in that particular case. Now this becomes, I'm not going to say more complicated, but you have to study a little bit more, and you have to study the same principle a little bit more when you are talking about inclined surfaces. Now let's say that you have I'm going to see if I can draw this somehow. Let's say that you have now this, and this is the same fish tank, but now it's changing, the bottom is changing. That means that if you have to study like a plate here at the bottom of that changing depth, if this point here is deeper, let me draw this from the side. So from the side, basically what you will have is something like this, and the depth of the water is going to be different. This point is this point, and this point will be that point over there. Remember, at the top the water is going to be the same level here. And let's say that this plate is laying here. Let's say, yeah, kind of there. Let's say this is what we have there. Well, look what is happening here. Now this point and this point are subject to different pressures. Why? Because they are at different depths also. Now if you measure the depth from this point to here, and you can call this, I don't know, H1, or let's measure it in Z. Let's say Z1, this depth, and let's measure this other depth, and let's call it Z2, that depth over there. That means that this plate is going to be subject to two differential pressures. If you look at the volume here, the pressure is going to be bigger in this part and smaller in this part, something like that, because it's changing like that, and that's going to be a volume in this part, like that, a volume of pressure. So, but the principle is the same. What is going to be the resultant force? The resultant force is going to be the resultant from that volume, and what is going to be the location? The location is going to be the centroid of that volume also, or the center of pressure, which is called in this case of that volume. Now if you simplify like that, basically what you have is that and remember that pressure is considered to be acting normal to every point. So if I go to this plate, this is gonna be one pressure, and this is gonna be the other pressure, and this is gonna be the distributed load on top of that inclined flat plate, like that, where this value here is the pressure corresponding to that point. And remember, if we have gamma as the unit weight of the liquid, then the pressure corresponding to this point is going to be gamma H, gamma Z2, in this case Z2, and the pressure at this point is going to be gamma Z1. I'm just working in one of the sides or one slice of this plate in that direction. Now if you want the total one, remember you have another dimension going in that way, then you multiply this times B and this times B. That will give you the total phase of this side, and multiply by B if B is constant. But you can work it all the time without this, and then multiply it at the end if you want to. Now the resultant of this, well, same thing. This is going to be a rectangular load, the triangular load. You calculate the resultant of the trapezium. What is going to be the total force? The resultant force is going to be the combination. You calculate the centroid of that one. Resultant force, you can combine this. If you don't know where the centroid is, you can combine this and this. Remember, this is 1/2 of the base, and this is 1/3 from this side here, not the base, whatever you call this distance. We call base the other one, but whatever you call this distance, and then you combine both of them, and the resultant force is going to be the area. Perfect, there's no problem with that. You have the inclined plane. By the way, this is cool because I do it like that, but there's also another way of doing it, which is, I don't know if easier, but some people see it easier. Let's say that you have the same situation, incline over there, and you have your plate here, and you have the height of the liquid here, and you want to calculate what is the height, the pressure over this plate. Well, you can assume that is that, but if you want to also, you could convert that load in several loads. For example, you can start with this and with this, and then you can say, oh, look, here is the same thing as having a load like that acting in this direction, where this point is gamma Z1, this point, and this is gamma Z2, and this is acting in that direction, and the resultant force is going to be somewhere in this direction for this force. So this is going to be the same pressure here and the same pressure here, but now it's acting horizontally instead of acting inclined like that. Now on top of this, because everything is acting at the same depth, this is going to be gamma Z1, this is also gamma Z1, and this is gamma Z2 here. So you have this pressure, you have this pressure also, and on top of that you have another load, which is the weight of this triangle or this prism, because I'm doing it flat, but remember that has a dimension in that way. The weight of this prism, which is just this distance times this distance divided by 2 multiplied by gamma of the water, and it's acting here, the weight of that part, which is acting here 1/3 and 1/3, and then you combine all of those forces over that plate if you need to do it like that. I'm gonna build some examples later that you are gonna apply this part. What else can we do? Okay, now instead of being the flat plate like that, now it happens that the plate is curved, following any shape. So you have something like this, and this is at the bottom of some fluid or submerging some fluid, and then you have the same situation. This goes in that direction, this goes in that direction, this goes like that, and this is the plate. Now it's a curved plate, and remember, all of this is submerged in some liquid. The principle is the same. You calculate this depth here and this depth here at the top, at the bottom, and then what happens is that instead of being a flat plate like that, now we don't have that flat plate, but we have a curved plate. But the principle is the same principle. Now we have a curved load, which is acting always perpendicular to that plate, something like that. Now instead of doing this, because you can do this by integration, by integrals, and calculate this same thing, the same way that you calculate the centroid, and the same way that you calculate the area. Remember how to calculate the area? In order to calculate the area or the volume that you multiply later by the b, it's just the integral of the differential of area, and that means that you have to leave the equation, find the differential of area, and in order to calculate the location in x or location in y of the force, is going to be what? The xi dA divided by the integral of dA, and then y bar equal the integral of y dA divided by integral of dA. This is the same thing that we did before for this, but instead of doing it like that, you can also use the same approximation. I'm going to use just the flat surface like that, and instead of going through the integral process for that, you can use this approach. You can have the load coming from, let's say this is submerged at this point, and this is the plate. This is the depth, this is the depth. Well, the first load that I can find here is a rectangular load coming from this depth. This is the depth Z1. What is the value for this one? And remember, I'm just doing one slice. If you want the total, you multiply by the width, by this. What is this? This is going to be gamma Z1, that rectangular load. Now, at this point, you have a triangular load here. But the triangular load should start from the top. Now, the only part that is acting through this submerged object is this part. That's why you have the trapezium acting in this direction. What is this? This is gamma Z1, same as this one. What is this value? Well, if we call this Z2 as we did before, this is going to be gamma Z2. And now you can calculate the resultant, the horizontal force here, resultant horizontal for that, the resultant vertical for that load. And on top of that, you have this weight coming from this volume or this area of water here, or of liquid, which is just the area or the volume of that, depending on what you're using, multiplied by gamma of the liquid, and it's going to be the weight, right? This multiplied by this is going to be the weight, and the weight is going to be acting at the centroid of that shape. That's the weight of that shape. If you call this, I don't know, A, B, C, well, the weight of the area ABC is going to be acting there. And the resultant force can be calculated by combining all of those. Now, application of this, we're going to see it soon. Right now, I'm going to do a couple of examples in a video. But now imagine that in a real case scenario. What is a real case scenario? I don't know. You can have something like a submerged dam, for example, or earth dam, not submerged dam. You have a dam like that, which is a really cool example that we're going to do later. And the dam is designed for keeping the water, let's say, in this part. And this is soil. All of this is soil. And if you want to make it more real, you might have even also soil in this part if you want to, or part of soil in this part also if you want to. But we are not considering soil. It's the same principle for soil. This is going to produce also a triangular load coming in this way, like if it was water, but the soil has to be has to have friction, being granular soil, and then calculate coefficients which are called Ka or Kp, Rankine coefficients for that, and these coefficients are just multiplied by the same formulas for pressure. But this is not for statics, this is for geotech. But just imagine that you have this part here, and you have to calculate the resultant force or see how this dam can fail, forgetting about the earth. Well, this dam could fail if the pressure of water is big enough to do two things. First, it can slide it, and that could be easily studied if you want to, because if you apply the pressure here, it's going to be a horizontal force. What is going to be the horizontal force? Let's study this. Okay, if I do this and this starts from the top here, the first thing that I'm going to have, either I do a float acting in this way or I do it like that. I'd rather doing it like that. So I have a triangular force coming in this way, for example, and if this is H, this is going to be gamma H. Resultant force horizontal is going to be acting here, which is going to be gamma H times H divided by 2. And the distance from here to here is going to be 1/3 of H. There you go. You have that force over there. Now, on top of that, you have also the weight of this water, which is going to be this distance that you can call, I don't know, A if you want to. And this is H. So remember, I'm working by unit of length in that way. If you want the total, you need to multiply by that distance. Now what do you do with this? You say A times H divided by 2. A H divided by 2, that's going to be the area of this, right? A H divided by 2 multiplied by gamma of the water. That's going to give me the weight of this block. And the weight of that block is going to be acting here. What is that? On top of this, right? But it's going to be acting there. And what is this? This is 1/3 of A, and this is 2/3, 1/3, because this is the right angle that I'm studying, 1/3 of H in this part for this block. Now you have those two forces. What other forces do you have? Well, you have the total weight of this dam. What is the total weight of that dam? The area, if I multiply by that the volume, multiply by gamma of the material that this is made out of. Let's say that this is concrete. So you multiply the area times gamma of the concrete. And that's going to be a force acting in this way, which is the weight of the dam. Now, if you study the balance or the equilibrium of this whole system, the same conditions that we applied before apply here. Summation of forces has to be 0 for equilibrium, and summation of moments has to be 0 for equilibrium. Now, what summation of forces? Summation of forces in Y. Summation of forces in Y. What forces in Y are acting here? I don't know. This part, I don't care. But the part that is acting over the dam will be this force plus this force has to be equal to what? To the strength of this soil so it doesn't sink. You are not at this level yet, but that's one of the reviews that you do. Now, what is the other review that you can do? That the horizontal summation of forces in X equals 0. What is that summation of forces in X equals 0? Well, this force minus this, in case that existed. In this case, it doesn't exist, but this force has to be absorbed by the friction. And the friction is no other thing than this weight multiplied by the coefficient of friction between the dam and the soil. You could do that if you have the values, the data, but it's not anything complicated. You just need the values for the friction, which is affected by the friction and the cohesion of the material here. But once again, that's not at this level. And the other one that we can do is summation of moments equals 0, because these forces might make these to pivot, and if it's gonna pivot, it's gonna pivot over this point, like that. So summation of moments with respect to that point O, for example, has to be 0. And you can do that because you have this force of the weight of the dam acting here, this force acting here, and the one that is gonna try to overturn it is this one. That's a really common and cool type of examples that you can use applying pressure, fluids, even earth, friction, and equilibrium, centroid, center of mass, center of volume, center of pressure. And these type of examples I'm gonna do in the next video, which is gonna be just about examples. Thank you for watching, and see you later in the next video, or you see me in the next video.